looking at this like 4-bar linkage, so we had 3 moving parts and then 1 kind of fixed part, something that is not moving compared to the other stuff. On Wednesday, we won't have class, like we won't meet here. I'll be on travel heading down to Washington, D.C. But we'll be back on Friday. Take a day off. You can look at like this problem. The next problem is similar. Like this, in this case, we're gonna like derive what the equations are, like try to figure out what's going on, how do we solve this. Then the next run is just sort of like plug and play. Like you already have the equations, plug them in, solve for unknown values. But that's the goal for today, is figure out what are the equations, like how do we take something where we know how it's moving, but how do I turn that into like math equations that I can actually start to solve? Make some progress there. Sound like a plan? So it's 1 degree of freedom. That means if I know how fast one part is moving, I know how fast everything is moving. So if I know link 1 is rotating at 10 radians per second, everything else should be a function of how fast that one's moving. That's what, at least in theory, that's what it should be. So the question is, to start, we're just going to jump right in. How do I do that? Like what do I do with this information? Like I know there's 1 degree of freedom. I know it's constrained to move together. How do I write down those constraints? So take a minute. You can like think about it. You could do a Google search. Like you could ask ChatGPT, what are constraint equations for this kind of linkage? Yeah, take a minute. What do you think? Where do we start here? Okay. Yeah. We also have like yeah, we could. We have like an investor. Okay. The starting point. What ratio? What? Yeah, like when theta 1 is yeah, yeah. That's what I was trying to figure out. Yeah. Okay. Yeah.
Where's that R was 0? So the component is 0. The R the component is also 0.
The RC.
The determinant 0 is the one at the bottom left, right?
Yes. Yeah.
So isn't there supposed to be RC supposed to be lower than R?
It doesn't have to be, because in this case they're both like the y component is 0 for both of them. In that like general kind of drawing. like here. Sorry, it'll catch up with me in a second. But in this case, so if dy has a value, then it keeps dropping it down. Yeah, yeah. Yeah. So this is like the general four bar linkage kind of system, but in our case, L2 and L3 are both the same. They're both 1 meter, and then L1 quarter, and then O and C are right in line with each other. And yeah, and O to C, C to B, B to A are all 1 meter lengths. Yeah. Any ideas? How do we get to equations, like something that we can solve? So it's 1 degree of freedom. So how do I, if I have 1 constraint, should be able to solve this? How do I get there? How do I actually solve this other thing? Yeah, I think it might be, I think one of these things a little more than one, right? When you get D as far left as you can go. No, just want to go through general, like A to move around as many times as it wants. It's called a spin around. And then B is like where B is. Right? Where A is at. So usually like a so quarter, 1. So kind of looking at all the places that A can go. A can move around in a circle as many times as it wants. Point B is going to rock back and forth. It's called a rocker arm. So it's going to follow that path. Like, hello. So you can build a robot that waves for you because waving is so tedious. This would be the way to do that. And then if you look at like where is this link going, the middle of it is going to trace out that kind of weird egg shape sort of thing, like that, as we move around in a circle. We could. Oh wait, mess something up. We want to watch what happens. It'll take a second, just creating HTML animation. Just thinking about, there we go. Ooh, not what I was looking for. the I need like a axis equal. Anyway, looks kind of weird because the scale is off. It looks like it's changing the length. Anyway, it's more like this. That's what we're looking at. All right. So we have like some vectors on here given to us, right? And where these hinges are at certain points. So let's draw those out. Let's draw green for stuff that we know. Are any of these vectors like constant? Which ones are constant? Okay, yeah, so this one, oh, not that. So RC is constant. It's not changing direction and it's not changing magnitude. Do any of them have like constant magnitude? Yeah, so the RA is always the length of L1. So we're starting to get like some stuff that we do know. This is a general process that you can use for any kind of moving parts, but I'm going to draw a couple more vectors on there. And let's see if we can figure out anything else. Oops. And I want arrows. What are those two pink arrows called? Like, how would I label them? This was like homework 1, maybe the second question that we worked on of like, here's a vector. Is it RPQ or is it RQP? Like, yeah. ABCD? Something like that. Yeah, which one is it? BA, BC, BC, BA? Yeah, so we'll say like where is the point? That's our B, and then slash with respect to A. But yeah, but that's exactly how we want to do it. It's like somehow so R B A and R B C. So now I've got like RA, RBA, RBC, and RC. Do any of those have, we know RC is constant, just a constant value. What about RBA and RBC? Is there anything, do we know anything about those vectors? Their favorite snack, the TV show that they're watching, that they're binge watching right now. Magnitude. Yeah. So we do know like RBA, we know its magnitude, and we know RBC, we know that magnitude. So what this is like called a vector loop. So you can always, if you have moving parts, or you know the parts are kind of constrained together somehow, you can always try to draw a loop of vectors, and as long as it's a closed loop, then you can start doing some vector addition to figure out what are the equations for constraints. Like how do I describe like the math behind a constraint? Does that make sense? I mean, it doesn't make sense like right now because it's the very first time you're seeing it. But as we, so now we have our vector loop. Yeah.
You must be stopped if someone in the comments said you're muted. Yeah.
Am I still muted? Sorry. Thanks for. Is it still muted? Have you heard back from your friend? Is that?
Yeah, that's him.
Oh, that's him. All right. I mean, according to. Hey, here's the sound. It seems like it's recording something, right? Like the sound bars are bumping.
I told him to
Turn on sound. Well, I'm not saying that it's definitely not his fault. Like it could be me, but I think I'm doing things. The green bar is moving. I don't think so. No, don't blame the user. The system is usually at fault. All right, we'll give it a shot. See if you can hear it, Lorenzo. Sorry. I think we're back. I think we have some sound. It'd be sad if we missed all of this like awesome content, all these views and reviews. No, my followers. All right, so we'll see if the sound comes back. Can we say anything about these vectors? Like, what do we know about those vectors? Yeah. Okay, what about them?
Okay, those ones, their magnitude is relative constant, direction is not.
Yep. So RBA, RBC, we know those are constant. Cool. He might have given up on me. Could be the problem. Crazy professor doesn't know how to use YouTube. All right, so we know some. What about vector equations? What do I know about the equation? Adding, subtracting, multiplying, any of those? Division's weird. We don't really divide vectors. But add, supply, multiply, we do those. What do you think? Yeah. Yeah. Okay. Can we say RB is RA plus RBA? Tip to tail adding, right? Cool. Is that the only way to get to RB? Yeah. RC plus RBC. Two different ways of getting to the same exact point. Both of them have like at least something that we know, like a little more information, because the point RB is going to keep changing. Like it's moving along that arc. We don't really know where it is. Technically we do know, but we have to do math to get there. No, not math. Believe it or not, this is like a huge amount of progress, because now I have two equations that I can set equal to each other. BA plus A equals BC plus C. How many equations does that give me? Because really right now, it's kind of this problem of like, if I know theta 1, if I know like what theta 1 is doing, I should know something about theta 2 and theta 3. So I have one known value. I'm trying to solve for two unknown values. So how many equations did I just get with this vector equation? 3? 2 or 3, yeah. Could be 2 or 3. Maybe 2. 2. Because at least like in a plane, if we're just talking two-dimensional, because everything is like three-dimensional objects in general we usually work with, but if they're moving in a plane, then we don't really care about their third dimension of whatever it's doing. We're just trying to figure out planar. So now we've got two equations for two unknowns. That's good. So vector equation, this vector set gives us like two equations. And now I'm going to copy this down. Zoom all the way into I know RA has to be L1. Its magnitude is L1. It's going to have some unit vector describing where it's at. What is that unit vector? Where is it pointing? Yeah, so that is RA. That one is the actual vector. Yeah, we could divide by L1 to figure out what it is like that thing. Yeah, we could say that it's like x over L1, y over L1. Like whatever, or XA and YA, right? You know what that's describing? Adjacent over hypotenuse, opposite over hypotenuse, sine theta 1. Which one's sine, which one's cosine? Opposite. So we'll call this one sine of theta 1. So I'm doing this because I want, at least I'm thinking ahead, like to the next step. Like I need some equation with thetas in it because I know theta is changing, so I need some way to relate theta 1 change to theta 2 change and theta 3. So if that one's sine, the other one's got to be cosine in our nice two-dimensional flatland. Cool. Do I have to worry about like what quadrant it's in? Quadrant 1, 2, 3, 4. Like positive and negatives and all that. Are we good? No worries. Either. Not worried. Maybe worried. Then we need these other two parts as well. Like what is BA and what is BC?
So one of the values would be negative, I think.
Yeah, like RC, this value of theta, this is definitely like a negative. Like we need to step backwards. But we're in quadrant 2, so cosine of like 90 through 180 is all going to give us negative x values anyway.
Yeah, no, my only thought is since we're just looking for the scalar length, which is a zero natural value, or is it just sort of?
Oh, well, the nice part is like if I take absolute value of this, it's equal to L2 times cosine squared plus sine squared, which is 1. So that unit vector that we just, whenever we use like cosine and sine to describe a unit vector, it's already, the magnitude is 1. So whatever we multiply it by, we're good to go. Yeah. Yeah, that was good. Looking good. So now I can take all those I components and all the J components and set those as like, okay, these are my constraint equations. And remember our and then I guess we'll put RC on there so everything's in one location. So try this out. Try adding up just the I parts and then just the J parts. And we'll see what equations we come up with. And while you do that, I'm just going to do a quick check. Hello. Do we have... There's definitely just no sound? I don't hear anything in the classroom. It says I'm... Oh, wait, because this is muted? There's sound, right? It sounds terrible. But there is sound. Is this me? I can see the frustration with why. You think it's just echoing? That was awful. Alright. I don't know. Hopefully we're getting something better than that. I don't think that would be very nice. as I was trying to help rewrite equations, I did not write them correctly. That should say RA. I don't know if that was a tripping point. Now you're like, it's all so clear now. Yeah.
Yeah, it would just be added, I mean, or multiplied by.
At least quick glance. Is it right? Or no? I hope so. Yeah. Yeah, we're just like grabbing just the eye. I don't think so. I was trying to keep simple steps rather than the first step. Give me an integration. That one. It takes a lot of like small, easy steps. Easy-ish. Yeah. How does that look for that first I? Any issues with it? Yeah. That one is because I have like this RC over here. That one is the I component of RC is 1. Yeah. So in the next equation, when it's 0, it's just they have to be equal to each other. Nice. Now we're coming up with like some real math equations, right? Like we knew they had to move together. Now we have like actual proof that this is how they have to move together. This is why these things have to do that. What is this equation telling us? Like, what is that J component thing? Like, this distance plus that distance equals that distance. What are those distances? The Y, right? So this is like one step up, L1 sine theta 1. This is another step up. So really all we did was say that if you go up by 2 steps, if you do it in 1 step, it's got to be the same amount. After all that, it's like, dude, why didn't you start there? Like, well, we got there. We got there eventually. And now we have like all these cool new tools to work with. Maybe not new, but like combining a lot of old tools into something new. That's what engineers do. Like take old stuff, jam it together, a lot of duct tape, a lot of WD-40, and now like, look, now we got something new. Now we got something cool to play with. And same thing for like the X. X is just like a little harder to see, but if I take 2 steps in the X, it has to be equal to the same 2 steps. Like, no matter how I get to point B on either direction, I gotta end up at point B. Are we any closer to speeds though? So theta 1 dot is 10 radians per second. We have 2 equations with thetas in them. How do I get theta dots in those? Like the d theta dt, right? Yeah. Yeah, we could like solve for everything in terms of theta 1. I like that. We could do that. Same I and J statement, right? We didn't change a lot of it, but what about theta dot? How do we get that one? Ooh, take a derivative. What do you want to derivative? What do we want to derive? Like if we want to take cosine inverse of everything, and sine inverse. Yeah. Or divide things, and then we have a tangent and a tan inverse. I hate inverse tangent stuff. Not to like, if that's like, but I love inverse tangent. It's like, that's fine. It's cool. It's a good function, but it just, if I can avoid it, I usually do. So I'm going to avoid it. But derivative should get it, right? Because if theta is something and theta dot is 10, then should be able to take a derivative. But what can I take a derivative of? Anything I damn well please. Derive whatever you want, right? So if this is my like constraint on position, the constraint on velocity looks exactly the same. The only difference is that RC, the change in RC is 0. So VC is 0. So we end up with like 1 less term there. So I can take derivatives of whatever, however I define position, I can take derivatives of it. And now I've got constraints on velocity. And that works for acceleration too. Acceleration, you can take another derivative of acceleration. That one's a little weird. It's called the jerk of the thing. Usually it's just your professor is the jerk, but You can also derive a jerk out of accelerations. Oh, we're almost out of time. Taking derivatives here, let's just do what is derivative of sine of theta? Theta is a function of time. Like if theta is a function of time, what is ddt of sine of theta? Cosine theta? Is that it? So it's equal, so the time derivative of sine theta is equal to the theta derivative of sine theta? I forgot about it. Yeah. So is ddt of sine theta equal to dd theta of sine theta? No, it's got to be different, right? Like there's something missing there. That one, oh, sorry.
If you were taking the derivative, we could also put in front the derivative of theta with respect to time, like d theta dt.
Yeah. So it's ddt is going to be dd theta dd theta times d theta dt. So it's a chain rule is the main thing. So we need first dd theta, like whatever's inside the function, and then d theta dt. So now I can say like L1 theta 1 dot sine theta 1 equals L3 theta 3 dot. And I know we're out of time, sorry, but I'll just write it up here so at least, even if the sound sounds like a whale, we do have a record of it. Now we've got constraints on velocities, I and j component velocities. All right, and then I'll see you again on Friday. I'll send out an announcement too to remind, but Wednesday, no class. Just take some time, think about the material.
Thank you.
Yeah, thanks a lot.